Okay, so good morning students. Today we will discuss the canonical ensemble in classical statistical mechanics, and this ensemble is in some sense more useful compared to the ensemble that we have studied so far, which is the microcanonical ensemble. So, the canonical ensemble is your first ensemble that allows fluctuations. In your microcanonical ensemble there were absolutely no fluctuations, it was an ensemble of constant n, v and e. In this ensemble I allow energy to fluctuate, thereby keeping temperature constant. Okay. So, this quantity T is kept constant by allowing energy to fluctuate. So, this is the first ensemble where some fluctuations are allowed. Okay. And just to help you understand, I will draw a schematic diagram of a system in contact with a heat reservoir, such as this room where I am sitting and the temperature is comfortably kept to 26 degrees centigrade by the thermostat, which is the air conditioner. So, let us say this is our room and I am calling this as our system at a constant n, v and temperature T, which is maintained by a reservoir, and the reservoir is purposefully taken to be much larger than the system, because I want the system to be driven by the reservoir, not the other way around. Okay. So, otherwise if you take reservoir smaller than the system, then the system acts as a reservoir to your thermostat. Okay. So, this is my reservoir, thermal reservoir, and I am allowing for an energy exchange between my system and the reservoir. So, let us say that my system at some given instant is in a microstate mu, okay, and the energy of this microstate is simply E. So, I am going to use subscript mu s to indicate this is a microstate of the system, and the energy of the system is E s, instantaneous energy. So, the difference between Hamiltonian and energy is the following. So, Hamiltonian is the energy of a microstate. So, in some sense it is already carrying instantaneous information of the system. So, if I have a microstate mu, I can say that the microstate has an energy which is E, but this is not an average energy. Suppose I know the probability of finding my system in that microstate, then the average energy is nothing but summation over all probabilities times the energy in that microstate. So, that is the difference between E and H. Okay. So, H is an instantaneous energy for a microstate, and if you have the information of your probability distribution of microstates, you can compute the average energy. That is the difference between energy and Hamiltonian. So, that is just a small digression. Let us get back to our problem. So, I am going to say that similarly my reservoir at some instant, at the same instant let us say, is in a microstate mu of r, and the energy of this microstate is E of r. Okay. And because the entire joint system which is my system plus reservoir is in microcanonical ensemble, because it is shielded from the surroundings okay. So, my joint system is in a microcanonical ensemble. I can say that the energy, instantaneous energy of my system plus the reservoir is equal to the total energy E that is fixed, which is nothing but energy of the system plus energy of the reservoir, which is fixed. Okay. Now, my system can exist in a large number of microstates and so does the reservoir. So, the joint system can exist in a microstate is in a microstate which is, I will say, a doublet of mu s and mu r. So, you have to jointly specify mu s and mu r to specify the joint state of the system. Okay. So, what I can tell is basically the probability or the joint probability of obtaining the subscript s plus r simply tells me it is the joint probability of obtaining the system and reservoir in some microstate mu s mu r, that is the system is in mu s and the reservoir is in mu r. Okay. Well, this is nothing but 1 upon total number of states accessible to the joint system at energy E total. If you recall our microcanonical ensemble discussion, if we know the total number of accessible states to the microcanonical ensemble at NVE, then the probability of finding a system in one of the microstates is just 1 upon omega, which is the total number of states. Now, the microcanonical ensemble here is the system plus reservoir. So, our total energy is E total. So, in some sense N total, V total, E total is the microcanonical ensemble here, and this joint system can exist in omega sub S of r, S plus r number of states. So, the joint probability of obtaining a system in a combination of mu s mu r is nothing but 1 upon the total number of states accessible to my system plus reservoir, and that is omega, okay, this big omega. So, I can ask now myself what is the, since I am interested in properties of my system, what is the probability of obtaining my system, you know, in a microstate mu s. You know that the probability of obtaining the joint system in mu s mu r is 1 upon omega s plus r, because omega is 1 upon omega s plus r is nothing but the total number of states accessible to the joint system, and each state is equiprobable, each combination of mu s mu r is equiprobable. So, this probability can be computed by Bayes theorem that we have discussed in the first chapter. So, what is basically being asked is nothing but an unconditional probability that my system is in microstate mu s. I do not care about which state my reservoir is, give me the probability of finding my system. If you look at the subscript, I am just using the subscript s, give me the probability of finding my system S in a microstate mu s, okay. And this can be answered by virtue of Bayes theorem, is that if I have the total joint probability, if you recall the Bayes theorem, then I can simply say that this is nothing but the joint probability or total probability of obtaining the system in this doublet divided by the conditional probability that my reservoir is in state mu r, okay, some reservoir provided the system is in this microstate mu s, because the left hand side requires information of probability of finding the microstate mu s. So, the denominator has to be a conditional probability of of finding a reservoir in mu r such that the system is at mu s. Okay. So, that is the so I will say that this is nothing but a conditional probability of reservoir in microstate mu r provided system is in mu of s. Okay. So, I can now write down my P of s, the probability, unconditional probability of finding the system in mu of s, as nothing but 1 upon because the numerator is nothing but 1 upon omega s plus r and some E total into the numerator is nothing but a probability of finding the reservoir or number of microstates in which a reservoir can exist with the energy E total minus the energy of the system at E s, provided the system state set, provided my system's instantaneous energy is E of s. Okay. That is the denominator, it has gone in number in terms of number of states, it has gone in the numerator. Okay. Now, you can think of it in the following way that this by virtue of Boltzmann's entropy, I can always write down my S as kb ln omega, if omega is a number of states. This gives me omega always as it always goes as e to the power s over kb. In fact, in this case I am always write down the equality here. So, I can write down my probability in terms of entropy as simply proportional to, because there is a denominator which is constant, okay, just e to the power entropy of the reservoir, which is a function of E total, reservoir is now in the energy E total minus E s over kb, okay, because my numerator is omega r, and you can write down that omega s of s plus r, the total number of states accessible to the system is a constant. Okay. So, I can write down my probability of finding a microstate in mu s as simply proportional to e to the power s r over kb, and this is s r, which is the entropy of the reservoir, and reservoir's energy is E total minus E s. And you can you can basically say that this I can write down this P of s mu of s as simply proportional to e to the power. I can expand the numerator in powers of as a Taylor expansion. So, in powers of the energy of the system as simply S of R as a function of E r. So, I am going to expand the entropy around the reservoir energy at E r equals to E total. So, that will give me the leading term, plus I am going to write down minus E of s, which is nothing but because we are talking about instantaneous energy, E of s is nothing but minus of h of mu s, okay, into delta S r over S E r at E r equals to E total, plus higher order terms which I am going to drop because they are at least quadratic in powers of the Hamiltonian of the system, and that is very small compared to the energy of the system. So, I am going to drop it. Okay. So, we are going to basically not consider terms quadratic and above in the powers of the system's energy. Okay. So, this can be simply written as I can take this P of s mu s as simply proportional to e to the power S r E total over k b into e raised to minus h mu s, and ds by dE is nothing but the temperature of the reservoir. So, I am going to write down from the thermodynamic definition of temperature that this quantity is nothing but 1 upon temperature of the reservoir. Okay. So, now you can simply upon kBT of course. Okay. So, you can simply say that the probability of finding the system in a microstate is simply equal to e to the power minus beta h mu s okay. You can think of you can basically substitute this beta as 1 upon kBT and look at the fact that I have converted the proportionality symbol into an equality, which means I am going to divide this entire thing by summation over all microstates e to the power minus beta h mu s, so as to normalize it to unity. This quantity is a constant because E total is fixed. So, it just cancels off when you take the summation over all the exponentials, it cancels off in both numerator and denominator. Okay. So, let me just maybe because it is appearing as too sudden, let me do it in 2 steps so that there is no confusion. Okay. So, I am going to simply to make things simple do this in 2 steps. Okay. So, I am just going to maybe rub this off and simply write it as a simply I will write it as some constant into e raised to minus beta h mu s, and the final step I am going to say that I have summed over all to normalize it. Okay. I am going to simply write it as e to the power minus beta h mu s over summation over all microstates e raised to minus beta h mu s. So, this is basically after normalizing P of mu s. Okay. Now, let us call this as some equation 1, we have not labeled any equation so far. Now, this quantity is basically, the denominator is basically nothing but the partition function. So, we can actually write down this rewrite this for the sake of convenience as e raised to minus beta h over the canonical partition function at n v n t. So, let me with your permission not call this as equation 1, I am going to call this as equation 1. Okay. So, where this canonical partition function has been introduced. Just to remind that the macro state here is NVT. So, the our partition function depends only on the macro state, and it is nothing but summation over all the micro states of our system of this Boltzmann factor e raised to minus beta h mu s. This is the definition of the canonical partition function. Now, I am going to transform my probability distribution from microstate world to the energy world. So, I am going to write down this PDF in terms of energy E. Now, the reason why I want to do it is because a large number of microstates may be degenerate, may be sitting at the same energy. Okay. For example, if you look at so, I am going to write down the reason as you know this basically this construction is more helpful or more useful as a large number of microstates are degenerate. So, it is more helpful to look at the system from the viewpoint of energy rather than the microstate itself. So, you may ask yourself a question, which energies are more probable and which energies are less probable, instead of looking at the microstates themselves. So, the simple reason is if I take an ideal gas of particles and there is no potential energy, for example, then these particles are simply the energy of the system is simply kinetic. So, it does not matter if I translate the entire pair to which is moving in some direction, okay, with some velocities. If I translate this entire pair to some other corner, then I get a different there is another realization where the same velocities are possible, but the energy is same. So, the kinetic energy is same in both the configurations, but this is a different microstate. So, you can consider a large number of such microstates which correspond to the same energy, and I am not interested in those microstates, I am interested in the energy distribution. So, I am going to transform my probability density probability distribution function from microstates to energy. Okay. So, that can be done very easily by saying that if I want the probability distribution function in terms of energy, I can write it as since I have already used big E as a total energy, have I used it? No, I have used E total as the total energy. Okay, fine. So, E here is the energy of of the system. Okay. So, you can use a different symbol here, maybe because we have used the instantaneous energy as ES. So, I am going to use some. Okay, so let me use E itself. So, here is the energy of the system. Okay. And I am now going to drop the subscripts mu s, because now everything is related to a system. So, I am going to drop the subscripts here, because we are only dealing with the system properties here. Okay. So, you can drop the subscripts purely for convenience. All quantities are now referred to as the system quantities. Okay. So, why do we keep S? Fine. So, I am going to simply drop these subscripts. Because henceforth all quantities are system quantities. So, this is nothing but so if you want to find out the PDF in terms of energy, what you have to do is basically sum over all microstates of the system, okay, P of mu, okay, and simply use the condition that whenever the energy of the system becomes E, you take a count, and when it does not equal to E, you do not take a count. So, this is basically just a canonical delta function, which when weighed in your PDF P of mu, it gives you P of E. Okay. So, I know the sum of all E's should be 1. So, the right hand side simply tells me that I have to sum over all mu and sum over all E. For each E, I will sum over all mu, and that will give me P of E, and when I sum over all E, I should get 1. Okay. So, this will simply become if I substitute our expression for P of mu, which is nothing but e to the power minus beta h of mu over the partition function that I am going to take outside. Okay. So, I am just going to, maybe for the time being, I am going to write down this partition function in the denominator. Into delta of h mu E. Now, you can see that a large number of microstates that have energy E will contribute to this sum. So, first observation is that the partition function will come outside, because it remains as is, does not matter whether you use the probability of finding the system in a microstate mu or you find a probability in terms of E, partition function remains the same, and that summation simply captures all the states with energy E. So, I am going to say that this is omega with energy E, and e to the power minus beta E. Okay. So, wherever h mu was E, I picked up a sum and I had to take e raised to minus beta h mu as e raised to minus beta E. How many times I did it? Omega E times. So, omega E here is basically is the number of So, every time this delta function picked 1, I have counted 1. So, it has picked 1 omega e number of times. So, this is the number of microstates where the energy of the microstate was E. Energy of the microstate of the system was E. And so, now since by virtue of again Boltzmann's entropy, I can write down my omega of E as e to the power s over k b. Okay. So, my probability distribution function in terms of energy simply becomes e to the power minus beta E minus s over k b t. Okay. The 2 minus gives you plus. I think I have to, yeah. So, there should be correct. So, I have to I have to write E minus T s, because beta itself is 1 upon k t, t cancels with t and you just have 1 upon k b. Okay. But from thermodynamics I know that this is nothing but e raised to minus beta into free energy. Okay. Since our free energy, thermodynamic free energy or your Helmholtz free energy is E minus T s. So, of course, I am missing a partition function here. Which normalizes everything. So, our partition function that we have obtained in terms of microstates was nothing but summation over all mu's e to the power minus beta h mu. So, if you have all the microstates of a system, then the Hamiltonians will give the information on the partition function, or in other words, if you have all the energy states in which the system can sit, then the partition function can be computed as e raised to minus beta into free energy for that energy, because this will normalize your probability distribution function P of E. Okay. So, the second definition of partition function here follows from here. Okay. So, I have to take the form of Z as summation over all energies e raised to minus beta f, because the numerator is e raised to minus beta f. That is the normalization I want to use to make my P of E normalized. Okay. So, now I can write down this as the normalization required. So, the partition function is the normalization required to basically keep the probability distribution function well behaved. Okay. Because we want summation over all energies P of E to be 1. Okay. All possible energies that my system can take, if I sum over all the probabilities, it should be 1, as shall be the probability of finding a system in a microstate. Okay. We break here, and when we come back we shall continue the discussion. Okay. Thank you.